the wavelength in nanometers of electromagnetic radiation with a frequency of 5.37 times 10 to the 14th seconds to the minus 1. So our symbol for frequency is the lowercase Greek letter nu, which looks like a V, except with a hat on the back. And this is how I draw it. And for the equation that we need from our conversion and equation sheet, the equation is going to be right here. And so on your equation sheet, the frequency symbol looks a little different, but hopefully, and then you can see the frequency in two different equations. The equation that I'm pointing at right now in the conversion equation sheet is the one that we're going to use for this problem. And it goes like this: C equals lambda times nu, where C is the speed of light in a vacuum. And in this class, we're going to use the speed of light and, as I called in the lecture outlines, the speed of all electromagnetic radiation, not just light, is 3.00 times 10 to the 8th meters per second. What I'm going to do is I'm going to go ahead and start filling this equation in. So C is 3.00 times 10 to the 8th. Meters per second. That's going to be equal to our wavelength, which is what we're solving for in this problem, times our frequency, which is 5.37, times 10 to the 14th. And that's in units of seconds to the minus 1, which another word for seconds to the minus 1 from the lecture outlines is going to be hertz. And if you have any questions about that, let me know. Now all we have to do is we have to solve for wavelength here by dividing through both sides by the frequency. Oh, sorry. I made a mistake there. This is 10 to the plus 14. I accidentally put a minus sign there, so I'm going to correct that. That's going to be a plus and a plus. And I'll leave this as seconds to the minus 1. We can cancel that out, cancel out our units, and we see that we've got wavelength on the right-hand side, and we have to do the math here. Let me do the math, and then we'll talk about units, because this problem does ask for the answer in a specific set of units. So 3, I don't have to enter the 0.00, exponent 8 divided by 5.37 exponent 14. And I get a number, let me put it into scientific notation here. 5.59 times 10 to the minus 7th. That's going to be my answer to 3 significant figures. Let me write that down, 5.59. So wavelength equals 5.59 times 10 to the minus 7th. That's the number as far as units go. So we can see that we have meters, and we have meters per second, and seconds to the minus 1. And we know that seconds to the minus 1 is 1 over seconds. So let me write that up here. So these two are two different ways of saying the same thing. So those can get canceled out. And we're left with meters as our units, which is not what we've been asked for. We've been asked for nanometers. Can anybody tell me how many, what the relationship is between meters and nanometers? So 1 nanometer equals what?
1 billionth of a meter.
Thank you, Selden. 1 nanometer equals 1 billionth of a meter, so 1 times 10 to the minus 9 meters. And then we can make the unit conversion using my usual method. So we're going to want meters on the bottom. And nanometers on top, showing that we have to divide by 10 to the minus 9. Let me show you how to do that, and then we should have our answer. 5.59 times 10 to the minus 7 divided by 1 exponent 9 minus, and I get 559 as my number, and that's going to be 559 nanometers. This coincidentally or not coincidentally is in the visible region. And the visible region, as we talked about in the lecture outline, is generally considered between 400 nanometers and either 700 nanometers or 750 nanometers. I typically go with 700. Different people go with 750. And so this is in the visible region, not that that's part of your work for this problem. Any questions about this problem? Okay.